Okay. So, now we have derived that transfer function of lossless tube without considering any loss, infinite power at 500 hertz, 1.5 kilohertz, 2.5 kilohertz. Now, if I consider that the tube, the wall which I suppose to be rigid, if this wall is not rigid, this wall can flexible, this wall can modify if pressure is high. If there is a pressure, wall can change. So, what is happening? Instead of cross sectional area A is fixed, now A is also function of x and t. A is also function of x and t. So, anytime the cross sectional area A x t is nothing but a average area, or you can say the A x t plus delta change of A x t due to the pressure at that position and that time, delta A. So, if you see the slides, I have the slides is there. So, inside it is A 0 t, I can say it is A 0 t fixed, and then it is delta A x t is expansion. So, now if I instead of u A and rho A, the wave equation I have modified, because the wave equation instead of fixed A is modified. Then if I put this one A 0 x t into del A x t, where A 0 x t, then the modified equation will be like this. So, I am not going details modified equation mathematical things, then it will be take lot of time. So, this is not that objective to derive the details. Details can be available in the papers also, mathematical details. So, there is a complex equation will come out. If I see the complex, so I can say this tube is made of a muscles. I can say muscle is nothing but a spring mass action. So, it is nothing but a spring mass mechanical oscillator. If I consider the second order equation of the spring mass mechanical oscillator, then this will be like this. Then again if I 1, 2, 3 if I consider, and then the wave equation instead of 2 wave equation, this 3 equation will derive, and from that 3 equation I get an analytical solution of what will happen in the frequency response, which is V A omega u L omega divided by u g omega. Now, they said if the length of the tube is 17.5 centimeter and 5 centimeter square is the cross sectional area, and m omega is 0.5 gram per centimeter square, b omega is 659, that means m omega is nothing but a mass per unit length, b omega damping per unit length and stiffness per unit length of the vocal tract wall. Okay. If I consider that value, then it is said it was found in the frequency response. Earlier it was infinite energy 500 hertz, 1.5 kilohertz, 2.5 kilohertz, like that. It is said that complex pole with non-zero bandwidth. So, here it is 0 bandwidth, here it is 0 bandwidth, bandwidth is 0 in tube lossless condition. Now, if I introduce the loss, what will happen? Then instead of 0 bandwidth, some bandwidth will be generated. So, the poles are complex with non-zero bandwidth, slightly higher frequency. The frequency will be Forward instead of 500 hertz, it may be 505 hertz. Slightly forward frequency is shifted towards the higher frequency side, most affected in the lower band. Lower frequency will be the most. So, lower frequency bandwidth will be increased more compared to the higher frequency. So, most affected is the lower band. Okay. Now, if I consider, so I said that earlier I have not considered the friction loss, viscous loss and thermal loss. Now, if I consider the all kinds of friction loss, thermal conduction on the wall, viscosity, all kind of losses, then I found it increased the bandwidth of the complex pole and decreased the resonance frequency slightly. So, ultimately I can say that yes, if I consider the losses and not residual. So, instead of a infinite zero bandwidth infinite impulse at every resonant frequency, it becomes a finite bandwidth with a slightly shifting higher direction of the formant. So, formant is shifted slightly higher direction. So, instead of this figure, ultimately I will get some bandwidth kind of formant, but if you see more or less it will be on and around of 500 hertz, slightly shifted. So, I can easily say normally if it is tube is totally open, first formant is 500 hertz, second formant is 1.5 kilohertz, third formant is 2.5 kilohertz, third formant is 2.5 kilohertz, fourth formant is 3.5 kilohertz, fifth formant is 4.5 kilohertz. Okay. So, now if we see if a signal is band limited with 4 kilohertz, then I can say I only can get up to fourth formant. I cannot get the fifth formant, because fifth formant 4.5 kilohertz. So, I will not get it. Okay. So, if I cut the signal in here, I will get only 3 formant. If I cut the signal in there, then I will get the 3 or 4 formant. So, depends on the sampling frequency, formant will come. I will come, this will discuss later on also. Okay. So, I am not details discuss about this kind of losses. Now, second difficulty is the effect of radiation at lips. So, what I said, once the air is radiated from the mouth. So, I can say at the opening of the tube, the acoustic wave is radiated. So, the radiation, this radiation, where it is radiated? In the atmospheric air. So, what will be the radiation losses? What kind of effect I will get due to this radiation? Okay. So, now if you see the assume that PLT is equal to 0 at slip, this is the we have assumed the acoustical analog a short circuit, the output when you couple this thing, if I say transmission line, I said the output is totally short circuit. P is equal to 0 T means the voltage is equal to 0. So, output is short circuit. Here I said there is a no load, no acoustic load. So, it is load is 0, output is short circuit, it is ideal condition, but it may not be the ideal condition. So, what will be the effect of air load on the lip, or you can say the radiation effect on the acoustic wave transmission. So, then if I put the microphone, then I can say what kind of signal I am expecting from the mouth. Okay. Now, if I consider that, how do you do that? So, I can say this is the tube and this is the mouth. Here it is radiated. So, whole load is the atmospheric load is there in the lip. So, the load is nothing but a inductive and resistive load, LR and RR, acoustics mass, inductive load and resistive load. Okay. Now, if it is there, then I can say here it is PL omega is nothing but a PL omega is nothing but a this load constitute a ZR. So, ZR into U L omega. So, I have not writing small u, it is keep it capital U, L omega means length, omega means instead of time it is frequency, it is length and frequency, capital P, frequency response. P L omega is nothing but a ZR into U L omega, or I can say that P L omega P L T is nothing but a small p L T is nothing but a ZR into U L T. Okay. Now, what is ZR? ZR is nothing but these two are in parallel. So, J omega, you can say the J omega L R R divided by J omega L R plus R R, because inductance J omega L R parallel with R. So, J omega L R R R divided by J omega L R plus R R. Okay. Now, if you see, if omega is where omega tends to 0, at very low frequency, ZR is equal to 0. That means, the acoustics load in the radiation load in here is not there, it is totally short circuit, which is the ideal condition. We said PLT is equal to 0. So, the frequency response whatever we have get due to the considering the loss and that things, that will be remain constant, remain same. That means, that implies or that means that at low frequency components are not affected by the radiation load, because at low frequency radiation load does not affect the frequency response of the acoustical tube. So, low frequency are less affected. Now, if I say j omega or omega LR is much greater than RR at high frequency, much greater than RR, then I can say it is nothing but a RR. J omega L cancel. So, it is nothing but a RR. So, load is totally resistive. So, radiation load is resistive, means there is a loss, radiation loss. So, I can say high frequency are affected due to the radiation loss. Okay. So, I can say the frequency response which I will get after the considering the losses with the bandwidth, if it is passed through the radiation loss, then low frequency will not affected much more, but high frequency will be lost. Okay. So, I will explain it in here. If you see, this is the figure with the no loss condition at 500 Hz, infinite energy, 0 bandwidth. If I consider the wall vibration, then I say the bandwidth is increases, slightly amplitude increases in high frequency and bandwidth is introduced, and bandwidth in the low frequency are much more. Then if I say the viscous loss, friction loss consider, then again the bandwidth is increase the bandwidth and slightly decrease the formant frequency, it slightly increase the formant frequency. So, increase decrease, if I cancel out, I can say the okay, formant frequency is in around whatever 500 as I have get here, but bandwidth is here is 0 bandwidth. Now, if I consider the radiation loss, then if you see high frequency or resistive radiation, so this circuit, this will be suppressed. Okay. So, radiation loss, due to the radiation loss, high frequency components amplitude will be decreased. Okay. Now, if you see that also here also, then in mathematics H j omega transfer function of the tube is nothing but a P L omega divided by U g omega, which is P L omega U L omega. So, it is nothing but a Z r omega will be multiplied with the V omega. Z r omega is 1 or no effect if omega is very low. If Z r omega is if the omega is low, radiation effect is not negligible. If it is Z r omega is very high, then there is a lot of attenuation in the high frequency. So, frequency response of the Z r omega is nothing but like this taper. If the frequency increases, loss is increases. Okay. So, that is why if I see any speech signal, if you see the speech signal, it will look like that high frequency or amplitude are less, it is due to the radiation loss. High frequency amplitude are very less. Okay. So, this is the frequency response of the uniform tube. If I consider whole tube vocal tract is a single tube, then I say this is the frequency response, this is the transfer function of the single tube model, where the frequency response is that formant frequency are 500 Hz, 1.5 kilohertz, 2.5 kilohertz, but the response is high frequency are attenuated due to the radiation loss, and it is not 0 bandwidth because of the, if I consider the losses inside the tube. Okay. Now, so vocal tract can be characterized by a set of resonance that depends on the vocal tract area function with shift due to the loss and radiation. The bandwidth of the two lowest resonance depend primarily on the vocal tract wall losses F1 and F2, and the bandwidth of the highest resonance depends the highest frequency resonance depend primarily on the viscous friction loss, thermal loss and radiation loss. Because if you see, I said the bandwidth is most affected frequency or low frequency in case of wall variation in the wall. In case of viscous law, high frequency bandwidth are introduced. Now, next one is nasal coupling effect. Okay. This is oral one cavity I have done, this is the one cavity I have done. Now, if you see, you experience that this is a cavity and you produce a sound. Now, if I put a hole in here, sound will change. If you see the flute, there is a lot of hole in the top of the flute, and by pressing the closing the hole, I can change the sound. If you see that flute or saxophone, just closing the valve means I am closing the hole in the tube. So, if I put a hole here, you know the frequency response is changed, the tube frequency response will be changed. Okay. Now, in case of our case in vocal tract also, there is a nasal coupling in here. So, once the velum is open, so nasal coupling is coupled with the oral tract, tube structure is changed, frequency response will be changed. So, sound pressure the same as at the input of for each tube, the volume velocity is the sum of the volume velocity at the input to nasal and oral cavity. So, closed oral cavity can trap energy at certain frequency, preventing those frequency from appearing in the nasal output. So, if you think about when I am producing a nasal consonant or nasal sound, if my oral cavity is totally closed, then the air is coming through the nasal. Now, if the oral cavity is not totally closed, then the nasal and oral both cavity are. So, if I consider the nasal sound is coming in this path, then some pressure will be trapped by this oral cavity. So, that trap will produce some anti-resonance frequency. So, nasal resonance have broader bandwidth, loss is much more. So, bandwidth. So, in case of the formant bandwidth will be broader in case of nasal sound, and the anti-resonance will be there. So, I can say deep, if I say this point will be much more larger point, anti-resonance will be introduced. So, bandwidth will be larger also. So, compared to the oral sound, nasal sound bandwidth is larger. Okay. Now, I stop here, because next class I will start about the sound another topic which is called how the excitation will excited the vocal tract, then we will derive the two boundary condition which is as the lip at the glottis. After considering the two boundary condition, we will derive the total transfer function in digital domain and then try to implement is uniform tube model. Then you go for the multi tube modeling of the human vocal tract. Okay. Thank you.